Welcome to our course on mastering numerical method for partial differential equations with MATLAB. Today we will delve into the introduction of explicit fourth order Runge-Kutta method for partial differential equations with applications. The explicit fourth order Runge-Kutta method is a powerful and widely used numerical technique for solving differential equations. It offers a good balance between accuracy and computational efficiency, making it particularly suitable for variety of applications in science and engineering. In this session, we will pour the underlying principles of the method, its implementation in MATLAB, and a practical example of its application to partial differential equations. By the end of this lecture, you will have a solid understanding of how to apply this method to solve complex partial differential equations, enhancing your ability to tackle real-world problems using MATLAB. This is the lecture on explicit fourth order Runge-Kutta method for partial differential equations with application. In this presentation, we will explore the explicit fourth order Runge-Kutta method traditionally used for solving ordinary differential equations and extend its applications to partial differential equations. We will discuss the theoretical framework, derive the necessary equations, and demonstrate how to implement this method for numerically solving partial differential equations using MATLAB. Through practical example, we will illustrate the accuracy and efficiency of the fourth order Runge-Kutta method in solving complex partial differential equation type of the problems. Let's dive into the process and see how MATLAB can be utilized to achieve precise numerical solutions. Here we are going to start from the ordinary differential equation and how we can have the formula fourth order Runge-Kutta method for this type of ordinary differential equations. This is the general form. dy upon dt is equal to fty, and we are given at this place is the initial condition. For that, we have to compute first k1, which will be equal to ftn yn, k2 is equal to ftn plus h by 2 yn plus h by 2 k1, k3 is equal to ftn plus h by 2 yn plus h by 2 k2, and k4 is equal to ftn plus h yn plus h k3, yn plus 1, which is unknown, and on the left hand side, and on the right hand side all these parameters are known. Yn is known value when we have t is equal to tn, and corresponding to this initial condition we have all the values of k1, k2, k3, k4, and h is the step size. On the right hand side these values are known, and on the left hand side this is unknown. This is unknown, which can be easily computed, this unknown value, from the known value. And this yn plus 1 is when we have t is equal to time tn plus 1. So by using this approach we can easily find out this value for the future time when the current values we are given. Now we want to apply this Runge-Kutta fourth order method to solve a heat equation, and we choose here the example del u upon del t is equal to alpha del 2u upon del x square, and this is the initial condition. Here we are given ux0 is equal to fx. To apply this method, first we have to discretize the domain, and let the special domain we have is 0 to L be discretized into n intervals with the step size we have is delta x is equal to L upon n. Let uin represent the solution at special time I, and time step we have is n. Then by finite central difference approximation, the second special derivative we have is del 2u upon del x square approximate to u n I minus 1 minus 2u n I plus u n I plus 1 upon del x square. Now we have to put the value in the given heat equation, and the given heat equation will be reduced to in this form: dui upon dt is equal to alpha, and this is the value of del 2u upon del x square. So after discretization, we have to put the value in the right hand side of the given heat equation. And also you can observe that this part becomes now ordinary derivative of ui with respect to t, which is dui upon dt. Now in this equation, we can easily apply Runge-Kutta fourth order method to find out the solution. Now note that dy upon dt is equal to fty, and k1 is equal to ftnyn for Runge-Kutta method, and k2 is equal to ftn plus h by 2 yn plus h by 2 into k1. Now our heat equation reduces to in this form: dui upon dt is equal to alpha ui minus 1 n minus 2u n I and plus ui plus 1 n upon delta x square. So here we have to compute this value for partial differential equation, and that can be denoted by k1i. I is the index corresponding to I, and this will be equal to alpha. Now this will be the right hand side will be u I minus 1 n minus 2 u I n plus u I plus 1 n upon delta x square. But for k2, note this point very carefully. K2 is equal to, we have ftn plus h by 2 yn plus h by 2 k1, where h is the step size. But in the case of partial differential equation, this k2 will be converted into this form: k2i will be equal to alpha. Now note, compare this part with this value uni minus 1. So this will be ui minus 1 n plus, we have at the place of h we have delta t upon 2 into, we have is k1, but here we will have k1i, but here index is I minus 1. Note this point very carefully. At the place of I we have to use I minus 1. Okay, so this will be k1 and index will be I minus 1, and the second part, which is uni, this will be minus 2 bracket, here will be ui n plus delta t upon 2, and at the place of k1 we will have here k1 comma I, and now the value of this part will be plus ui plus 1 n plus delta t upon 2 into k1 I plus 1 and close the bracket upon delta x square. So we have to convert all these values of k1, k2, k3, k4 in this way. Now come to at this place. Similarly, as we discussed here, k1 is equal to alpha u n I minus 1 minus 2 u I n plus u n I plus 1 delta x square, and then the k2i we can easily find out the value is, you can see alpha u n I minus 1 plus delta t upon k1 I minus 1, then minus 2 u n I plus delta t upon 2 k1i plus uni plus 1 plus delta t upon 2 k1i plus 1 upon delta x square. Similarly, we can easily find out the values of k3 and k4. Just you need to replace k1 into k2. Okay, and here is k1i, here is k2i. At this place we have k1i plus 1, here is k2i plus 1, and this equation also we have corresponding to the same k4. Okay, so we can easily write the expressions for partial differential equation which we required, and after that this unknown value UIN plus 1 will be equal to UNI plus delta T upon 6 K1I plus 2K2I plus 2K3I plus K4I. And you can easily compare that the given formula for ordinary differential equation converted into for partial differential equation. So in this way we can easily write the Runge-Kutta method fourth order for partial differential equation. Now following these sequence of statement, this step we can implement to find out the solution of partial differential equation, which is heat equation, as we choose at this place, and we will implement it to find out the solution. We will write the MATLAB code corresponding to all these expressions. Now this is the MATLAB window, and here we will apply this method. And first we need to assign the values of the parameters. L equal to 1, we have the length of the rod, and T is equal to we have is 0.1, which is the total time. Alpha is equal to we are choosing here 0.01, which is thermal conductivity, and Nx is equal to we have is 100, the number of special point, and in the same way we have Nt is equal to 100. We are choosing number of time steps. Dx will be L upon Nx minus 1, a special step size, and dt is equal to we have is T upon Nt. Okay. Now we need to initialize the conditions. So x will be equal to we have line space, which is 0 to L, and this will divide nx point. U is equal to sine pi x. This is the initial temperature distribution, and pre-allocate the solution matrix we have is U is equal to zeros nx nt plus 1, and U colon 1 is equal to U. This will be the values of all the points at initial corresponding to this one. Okay, so when we have t is 0, and for 0 the index we have is at the place 1. So for all values of x we have this will be equal to U, and will be computed corresponding to this initial temperature. Okay. After that, now we will apply the time stepping loop, and that will be vary from 1 to nt. For loop will be applied, so n will be equal to 1 to nt. K1, K2, K3, K4 zeros vector for corresponding to all these will be generated for 1 to nx by using the zeros function. Then after boundary conditions, at the left boundary and right boundary the values are zeros. So u1 0 is equal to 0, and on the right boundary we have this is also 0. Now this part is important to discuss here, how we can implement our code to find out the values of K1, K2, K3 and K4. This is very quite simple to implement here. So here the first equation, which is K1i is equal to alpha uni minus 1 minus 2 uin plus uni plus 1 upon delta x square. This can be easily implemented in MATLAB. You can see here this is K1i is equal to alpha ui minus 1 minus 2 ui plus ui plus 1, and upon we have delta x square. So this expression is same as we have in at this place. Okay, just you need to compare the syntax which we are using for MATLAB. Okay, now this value after computed K1i, we have to update the temperature. So new temperature is U plus dt upon 2 into K1. Note this point very carefully how we are using. And now come to in the second, see here. So K2i is equal to alpha uni minus 1 plus delta t upon 2 K1i minus 1. So this value is incremented with this part. Okay, so this updated value we are using here. Come back in the address place. So u temp is equal to u plus delta t into K1, and K1 is this value which we store at this place. Okay, so K2i, note this equation very carefully. K2i is equal to alpha product u temp I minus 1 plus 2 u temp I plus u temp I plus 1 upon delta x square. Okay, so this value will be updated at this place for K2i corresponding to this one. Now again, the value which is computed at this place, we will update again u temp for K2. This will be equal to u plus dt upon 2 product K2, and this value will be used to update the value of K3, which will be equal to alpha product u temp I minus 1 minus 2 u temp I plus u underscore temp I plus 1 upon dx square, and the value K3 will be stored at this place. Again we will update u temp. This will be u plus dt K3, and by using this new value we can compute the value of K4, and the value will be stored at this place. Okay, then after computing the values of K1, K2, K3, K4, we have to update the solution. For I equal to 2 to nx minus 1, ui will be equal to, this is the unknown value and all these are known values. Okay, and the formula is same as we discussed in the slide. Ui plus dt upon 6, k1i plus 2k2i plus 2k3i plus k4i, and you note that here the loop starting from 2 to nx minus 1. This is important to discuss here also, as we know that this is, we have special domain. Here the index is 1, then we have is 2, 3, 4, and this is the last one nx. But at this point and at this point, these are the boundary values. Okay, and this is the second last point, which will be nx minus 1. Okay, so the loop we need to compute only the unknown values, which are the interior point, and for this point the loop will be for 2 to nx minus 1. So these values we need to compute. That's why the for loop we have to use the index from 2 to nx minus 1, since these values are known as boundary values. So all the values which will be computed will be stored at this place. U colon n plus 1 is equal to u. Okay, so this will be our solution at the current time step, and then after we need to plot the solution. For that we have to use the mesh grid xt will be equal to mesh grid x line space 0 to t nt plus 1. Okay, and the solution we will have as sub function is there, then x input, t input, and u transpose. X label is equal to x, y label we have is t, z label we have is uxt, and title we have is heat equation solution using fourth order Runge-Kutta method, grid on and box on. So this is the complete MATLAB program by using Runge-Kutta fourth order method for partial differential equation. And when you will execute these sequence of statement for this method, and we will have the solution for the same. You can see here after running the code. Yes, so this is the graphical output of our result by using fourth order Runge-Kutta method for partial differential equation. Okay, so in this way we can use Runge-Kutta fourth order method to find out the solution of any kind of partial differential equation, but here we solve heat equation. I hope that all these content which we discuss will help you, will support you to find out and to implement in the other type of problems which are associated with the partial differential equations. In conclusion, we have explored the explicit fourth order Runge-Kutta method for solving partial differential equations. This powerful numerical technique balances accuracy and computational efficiency, making it an excellent choice for a wide range of scientific and engineering applications. By understanding the theoretical foundation and practical implementation of this method in MATLAB, you are now equipped to apply it effectively to various partial differential equation problems. As you continue to refine your skills, you will be able to tackle increasingly complex challenges with confidence, leveraging the capabilities of MATLAB to achieve precise and reliable solutions. Thank you for your attention, and I look forward to seeing you the innovative ways you will utilize and explicit fourth order Runge-Kutta method in your future work. Thank you to stay connected with this lecture till the end.